Hi, I'm J.D. Harrington, Public Affairs Officer for NASA's Astrophysics Division in Washington, D.C. I'd like to welcome you to today's Google Plus Hangout, where we will discuss findings on an extraordinary gamma ray burst that happened earlier this year. This was a once-in-a-century watershed event, made all the better by having a large array of NASA telescopes and ground-based observatories that's seen it. On April 27th, this gamma ray burst explosion was designated GRB 1304-27A. It was basically a blast of light from a dying star in a distant galaxy. Now, it tops the chart as one of the brightest we've ever seen. A trio of NASA satellites working in concert with ground-based robotic telescopes captured never-before-seen details that challenge our current theoretical understandings of how gamma ray bursts work. Before we begin, though, and we get to our panel of experts, a few housekeeping duties are in order. We have 5 panelists joining us today. Each will give a brief rundown of their expertise in this area and how they were involved. Of course, we would love to get your participation in today's event as well. And you can submit questions on NASA's Facebook account, NASA's Google Plus page, and via Twitter by using the hashtag AskNASA. Now, this media telecon will be limited to 1 hour. Today's panelists include Charles Dermer, an astrophysicist at the Naval Research Laboratory in Washington, D.C. He's also the corresponding author of the Fermi-LAT and GBM papers in the Science Journal that came out yesterday. We also have Tom Vestran, an astrophysicist from the Los Alamos National Laboratory in New Mexico. He's the lead author of the Raptor paper in yesterday's Science Journal. We have Rob Priest, an associate professor of astrophysics at the University of Alabama in Huntsville, Alabama. Now, Rob is the lead author of the Fermi GBM paper and a co-author on the Fermi-LAT paper. We also have Gian Piero Tagliaferri. He's an astrophysicist at the Brera Observatory in Italy. He's also a co-author of the Swift paper in the Science Journal and the New Star paper in AFJ. And our last panelist is Sylvia Zhu, an astrophysicist at the University of Maryland at College Park. Sylvia is the co-author of the Fermi GBM paper and corresponding author of the Fermi-LAT paper, both in the Science Journal. Now, I'm going to ask the panelists to give us just a little bit of a background on themselves and trying to keep it down to a minute or so before we get into the questions and answers. So we'll go ahead and get started. Charles?
Hi, everybody. I'm Chuck Dermer from the Naval Research Laboratory. NRL is a 90-year-old laboratory that is involved in basic research, discovery, and invention for science, technology, and defense applications. What I do is support ongoing research in detector technology that is used not only for terrestrial applications, but to look at the stars and the cosmos. On that, I'm most interested in high-energy radiation physics, from blazars, gamma ray bursts, pulsars, neutron stars, all sorts of exciting objects that radiate the very highest energy radiations. And if you want to look at some of my technical writings, I've written a book with Govind Menon on the high-energy radiations from black holes. Glad to be here.
Thanks, Tom. Thanks, Charles. Next, we'll go to Tom.
Yes. I'm Tom Vestran. I'm an astrophysicist at Los Alamos National Laboratory. I'm the principal investigator for the Raptor network of telescopes, which are ground-based robotic telescopes that monitor the night sky and look for things that go bump in the night. And one of the spectacular things we found that went bump in the night was this very interesting optical flash from this gamma ray burst. And I'd like to tell you a little about that today. Thanks.
All right. Thanks, Tom. Rob, you're up.
I'm Rob Priest. I'm the professor of space science at the University of Alabama, Huntsville, which is a research university. I am a co-investigator in the gamma ray burst monitor for GLAST called GBM, and we triggered on this event in April 27th and sent messages all throughout the world, and we saw some interesting behavior in the first pulse of the burst and led to a nice paper on science. Thank you.
Thanks, Rob. And now we'll go to John Piero.
Yeah, hello. My name is Giampiero Tagliaferri. I am an astrophysicist at the Brera Observatory in Milan, in Italy, which is 250 years old institute. My scientific interests are in high energy emission of celestial objects, in particular X-ray emission of gamma ray burst and blazar. I'm also working on the development of new X-ray telescopes. And I'm the PI of the Italian participation to the SWIFT mission. And the reason we are participating in this mission is because my institute provided the mirror for the X-ray telescope of board of SWIFT.
Thanks. And Sylvia?
Hi, I'm Sylvia Zhu from the University of Maryland. I'm a grad student, which is why my shelves have less textbooks than everyone else's shelves do, or fewer textbooks. And I study the high energy emission from gamma ray bursts with the Fermi Large Area Telescope. And thanks to, like Rob said, the GBM triggered on this burst. So when the GBM first saw it, it said, hey, let's take a look at this burst for longer. And so the spacecraft went and looked at this burst for a long time, and thanks to the GBM triggering, the LAT was able to see it for a long time as well.
All right, thanks, Sylvia. As I mentioned, just to make sure that we are on the same sheet of music here, I'd like to start with the basics, if you would. As I mentioned earlier, 3 NASA spacecraft, as well as other ground-based telescopes, caught this gamma ray burst. So I'd like to start out basically with explaining what a gamma ray burst is. Who can take that one? Chuck?
I'm not sure who you're asking, but I certainly have a standard answer to that. A gamma ray burst, as the name implies, is a transient flash of gamma rays from some random direction in space. After decades of research, we found out that those gamma rays come from the birth of a black hole in most cases. There's still some argumentation. But this was only possible through the development of new ways of looking, because you have to reorient your spacecraft very quickly to see these gamma ray bursts. And so there's a new astronomy that's been brewing over the last decades where you have this rapid response that made possible all the great discoveries about this particular burst we'll hear today.
All right, thanks, Charles. There's going to be a lot of interest, I think, from people that want to know whether there could be any damage from a GRB. As a matter of fact, we got one query already that says, if the gamma ray burst had been pointed directly at Earth, how much damage could be done at the distance of origin to Earth?
Well, it really depends on how far away this gamma ray burst is, and again, we're already assuming that it's pointed at Earth, which is a very kind of unlikely already. With a gamma ray burst, with the gamma rays coming in, the atmosphere is mostly opaque to gamma rays, and so it absorbs the gamma rays. Which normally gamma ray bursts are really far away. They're far outside of our galaxy, billions of light years away. So chances are that's going to be far enough that it's not going to really affect us. If you had a gamma ray burst, for instance, in our galaxy, which we're pretty sure is not going to happen, but if you happen to have a gamma ray burst positioned in our galaxy pointed at us, you would get possibly electromagnetic pulses that might damage some electronics. You would get a lot of ionizing radiation, and you would, and in the long term, the gamma rays would start to destroy the ozone in the Earth, on the Earth. So then you'd have more other radiation coming through as well, and it would affect the nitrogen and create nitrogen oxides in the Earth's atmosphere, which is a sort of brownish color, would lead to like a nuclear winter, basically. But short answer is that's not going to happen.
Okay, I appreciate it, Sylvia. Can somebody explain, maybe you, Chuck, why is it important for us to study GRBs, gamma ray bursts? What do we learn from them?
That's a good question, but since it's a kind of a rhetorical question, I would just ask, what was the importance of discovering or studying uranium physics, which was the most esoteric type of particle physics in the 1920s? What was the importance of just understanding the reactions that take place in the center of the sun, the nuclear burning reactions? Well, we don't have to. You don't have to have an answer to that. We all know it changed the world. There's no reason to think this is going to change the world, but on the other hand, it's a fascinating system because it's an engine, an engine that converts one type of energy to another. It's the most efficient type of engine, and then it's an explosion. And so whenever you do explosion physics, you learn something that may, and hopefully in many cases may not, ever be used in terms of humanity, but it has intrinsic interest that could be applicable at some point, for example, the particle beams for the acceleration of the highest energy cosmic rays. So we don't know. That's what makes basic research. We're just trying to understand something for the very intrinsic interest of knowing about it. And maybe it will have applications down the line, but in the present day, it gives us a greater appreciation of all the activity that goes on in nature, which is a good use all by itself.
Okay. There's a tremendous amount of energy that comes out of these gamma ray bursts. Do we know the source of this energy? Where do we think it comes from? And I'm not sure who can take that one. Anyone?
Well, I'll pipe up here and say that in large part we don't really know. And the beauty of having a very bright burst like 130427A is that we can study its properties in great detail and compare that with theoretical predictions like made by Dr. Dermer, and see how everything fares with respect to the observation. And so we know one thing very clearly, that the gamma ray burst can convert energy very efficiently into gamma rays directly. And that seems to be the crux of the matter, and nature seems to be able to do it quite naturally. We have some ideas. Magnetic fields can, through the synchrotron mechanism, can efficiently convert energy into radiation, but we have to compare these ideas with the observations. In many cases, they fall flat.
Appreciate it. I think we're going to give this one to John Piero if we can. Now, I know scientists study the X-ray afterglow of gamma ray bursts, but what do they learn from doing this?
Well, the X-ray, the capability of studying gamma ray bursts in the X-ray band is crucial. In fact, it's thanks to the X-ray observation that we were able to identify the first afterglow associated to gamma ray bursts. And by doing this, we got the good position, and we could follow it in the optical and find the optical counterpart and their redshift. And therefore, for instance, we could immediately prove that these objects were extragalactic. And by getting the position and the redshift, we got the flux and the luminosity, and therefore we understood they were extremely powerful objects. And so X-ray have opened up a very good window. And also, if we turn in the afterglow, which is what is coming after the explosion of the gamma ray burst, most of the energy of the afterglow is going in the X-ray band, then there is the optical and the radio. But essentially, 99% of the gamma ray bursts have an afterglow in the X-ray band, while in the optical, only 60 to 70% have an optical counterpart, and we call it dark, for instance, gamma ray burst, because we couldn't find the optical counterpart. So the X-ray band is the most effective way to get a position and to find the afterglow and follow the light curves, and then to give this very important information to the other band for people to follow on with the other instrumentation.
Appreciate the answer. Sylvia, I think this one here is from you. We got a question about people relate this amount of energy, or more even, to atomic bombs. How many atomic bombs worth of energy do you think came from this type of explosion, if you were to try and measure that?
So I guess it depends on what type of atomic bomb you're asking about in the first place. But I did a little, did a little Wikipedia-ing to see what sort of atomic bombs we might be talking about. And the most powerful hydrogen bomb, for instance, that was ever released on Earth, released, let's see, about 50 megatons of TNT, like the equivalent energy of TNT. And so, but what that means is you would still need about 10 to the 30 of these bombs to create the amount of energy that was released by this gamma ray burst over the entire process. And I believe that is either a nonillion or a quintillion, depending on if you're using short scale or long scale. So I learned some new words today.
Okay. Now, do GRBs like this typically concentrate all their energy in one direction, or are they somewhat omnidirectional?
So
I can,
this is. Oh, go ahead.
oh, go ahead, Sylvia.
Oh, no. I wasn't sure if that was continuation, but it's not, so go ahead.
So this is Tom Vestrand. So yeah, we believe that the radiation from these explosions is highly directional. It's highly beamed. So in this particular case, the beam had to be pointing directly towards us. And these are relatively narrow beams measured in a few degrees or so. So it's a very finely collimated flashlight, if you will.
Okay. I'd like to talk a little bit about the individual spacecraft and how they were involved in this. So we're going to start, I think, with Charles and Fermi. I know one of these spacecraft, I'm not sure which one, was actually targeting this area and caught this gamma ray burst before, during, and after. So what kind of information do we glean when something can see it across the entire spectrum of the event happening?
Oh, it's the difference between monocolor and technicolor. Once you have multiple observatories, you can correlate one type of light coming out with another. You can see how they each behave separately. It just gives you so much more information. But for your specific point, I'm most deeply involved with the Fermi Gamma Ray Space Telescope, like Sylvia and Rob are, and that has two main instruments, a large area telescope and also a gamma ray burst monitor for searching for gamma ray bursts. So it has all sky directionality except to the extent that the Earth blocks it. So as a consequence, fortunately, the Earth wasn't blocking during 130427A. When it went off, it was detected, and it allowed, by onboard triggering and response, to slew the entire spacecraft to follow it, except for those periods when the Earth was blocking. But yeah, the use of multiple telescopes, like Jean-Pierre said, we wouldn't have the imaging to even know what the counterpart was without the highly detailed follow-up of the X-rays and the optical.
So are you saying basically that each telescope asset that looks at this brings different perspective on it as far as what, the electromagnetic spectrum?
Well, it's more than the electromagnetic spectrum. We're in a decade that's starting to open up multi-messenger astronomy, gravitational waves, neutrinos, so we're going even beyond electromagnetic. For this burst, we're still in the electromagnetic channels, and even within those channels, we're getting all this information that is correlated. It shows that they behave in different ways, which we interpret then to try to build this model of our gamma ray burst in such a way to explain these various behaviors. And we think there's this engine exploding, it drives out a jet, plows into the medium, it makes another separate high energy radiation component. And this is only possible by having these multiple detectors looking at different wavelengths.
All right. John Piero, can one of these gamma ray bursts happen in our galaxy? Is that possible?
Oh, yes, for sure. I mean, it is difficult to quantify how many bursts one can expect, but we can think that there could be one gamma ray burst like this one every, I don't know, between 100 million years or 500 million years. It depends. We think there will be one gamma ray burst associated to 10 to minus 4, 10 to minus 5, 1 BC supernovae, and we expect one of these every, I don't know, few hundred years in our galaxy. So these numbers are still, you know, quite uncertain, but the order of magnitude is that we can expect one of each every 100 million years.
Thanks. Let's pull Rob into the discussion here a little bit. How frequent are these kinds of GRBs? How many of them have been observed, for instance?
Well, we have a good idea from the orbiting Compton Gamma Ray Observatory, in which there was an experiment called the Burst and Transient Source Experiment, BATSI. That was an all-sky monitor in low Earth orbit in the 90s. And except for the Earth blockage, with BATSI saw the entire sky in gamma rays, and we could see with very good depth nearly the entire universe of gamma ray bursts. And so we can peg a number about 1 per day per universe. That's taking into account that some of the sky is blocked and extrapolating from the blockage. So the universe provides us 1 per day, but we don't know where it's going to be or when.
All right, once again, I'd like to remind everyone that's watching that you can take part in active participation of this Google Hangout by sending your questions to the NASA Facebook account, to our Google Hangout page, and also via Twitter by using the hashtag AskNASA. Sylvia, how can these gamma ray bursts actually affect us here on Earth, or can they?
They can if they're right in our neighborhood, if they're right in the Milky Way. But as Giampiero just discussed, we can sort of put a number on maybe, or an upper limit on maybe how many we might expect. And it turns out we don't expect really to see one in our Milky Way. But if they're close enough, I mean, again, they could be, they could affect the atmosphere by creating sort of more of by changing the contents of the atmosphere a little bit, by interacting with the atmosphere. And I guess that would be the main problem, is if you lose the ozone layer, for instance, and then you get a lot of radiation coming in at once. That's what you would be worried about.
All right, we have a question here from Ask NASA. Are there any future missions with updated detectors and technology planned for gamma ray burst science that are coming up? Anything you know of, anyway? I take that as we're not sure yet.
Rob Priest here. We're in kind of a climate where we don't really anticipate new missions in high energy astrophysics to that extent as a dedicated burst mission. We have 2 excellent observatories which are still in orbit around the Earth that have good lifetime, that's Swift and Fermi. So right now we're not anticipating a follow-on dedicated to gamma ray bursts.
There will be one in Europe, launched by the French people together with Chinese. They're expecting to launch a mission called SWARM in maybe 2016, 2015, if they reach an agreement.
Appreciate that. One of the questions we got from one of our Facebook pages is there a program in place to find a way to predict these types of events?
Let's just say that there have been lots of attempts to look at repetition, and but we seem to have an understanding of the sort of stars that will lead to a gamma ray burst. They're high mass, they drive off lots of wind, they're very bright and luminous, they're so-called Wolf-Rayet type stars. We have one in the galaxy, Eta Carina, that could blow at any time, but since by any time we mean within 10,000, 100,000 years, and there's no guarantee Eta Carina will be a gamma ray burst. But that's what would be the signatures of actually finding what might turn out to be a gamma ray burst progenitor star. But typically they're at such large distances that we can't even see individual stars. So the likelihood of any sort of program like that being approved is not very large, I think.
Well, we have another question here. Is there a possibility, I love these questions, is there a possibility that this gamma ray burst is a result of a antimatter annihilation, shredding light on symmetry?
Maybe I'm the only person here who made a model of matter-antimatter activity as a gamma ray burst, and the short answer is no. Basically, if you drive matter into antimatter, it's like when you drop a drop of water onto a hot pan or oil. It makes a sizzling layer between the two types of matter, and so you can't get lots of emission in a matter-antimatter scenario because they just drive each other apart. So antimatter, except for comets in the solar system, which is what I was playing with, won't work. And of course, that model is completely ruled out.
Okay. Tom, let's bring you in. Maybe you know the answer to this one. Question is there a star map available that pinpoints the locations of previously observed gamma ray bursts?
So
If you don't know, maybe someone else does.
So this is Tom. Yeah, we've plotted out the locations of gamma ray bursts, and it's isotropic. They come from any direction in the sky. And of course, as was mentioned earlier, we don't know when they're going to come. So that's the challenge of building observatories that can find these things in any direction at any time. You know when about one per day will happen, but the challenge is you don't know when and you don't know where. And so there's no sweet spot to look at.
Okay. I'd like to get back to the synergy of having multiple space telescopes and ground assets working with this. When one of these assets sees a GRB, what's the notification process to bring all the other ones online to look at that same general vicinity?
Well, this is Rob Priest. What happens is a dedicated server at Goddard Space Flight Center sends out notices to subscribing astronomers. We have an onboard trigger for Fermi and also for the Swift BAT instrument, and each of these is hooked into this service, and it sends multiple messages of refined localizations on the sky out to interested astronomers like Tom. And some folks like Tom have robotic telescopes that actually respond to these messages autonomously. Maybe he can address that.
Yeah, so we have robotic telescopes that pick up these messages off the internet in real time and rapidly slew to the position of the localized gamma ray burst. In fact, that was what was done here with the Raptor T telescopes. But the fastest that's ever been done is something like that takes about 10 seconds or so. So you miss one of the interesting observational challenges is to pick up those first 10 seconds of a gamma ray burst in the optical. And this particular event, we were lucky. We had a full sky monitor that was looking at the position that the gamma ray burst happened at even before the explosion occurred. And this particular event was bright enough that we could see it in these persistent full sky monitors to actually make measurements of this before even the world's fastest slewing telescopes could get there. So that's one of the things that's really exciting about this event, is that we got it from before all the way through the event development to the end.
Now, John Piero, if I could target this question toward you. As I mentioned earlier, once in a century event, but I think that was my own comment there. How often can we expect to see a gamma ray burst of this size?
Okay, I think the real question is how often can we see of this brilliance and distance? Because this burst is quite big. The luminosity of this burst is quite high, but it's a typical luminosity that we usually see in gamma ray bursts that we detect a ratio of 1 and 2. What is unusual for this gamma ray burst is that it has the same luminosity, but it was very nearby. We call it a ratio to translate in distance, it is of 0.3. And that's why it was the flux that we received from this source was so much higher than any other one. So to have a burst of this luminosity at this distance, we expect one every 60 years or so. This is what we can infer from the what we call the luminosity function of these sources, because we can derive from the luminosity how many of them we can expect in a given part of the volume of the universe. So it is very unique event, I would say, 1 or 2 per 100 years.
Thanks, John Piero. I'm going to throw this one out here. I'm not sure who should take it. Maybe Tom, this could be yours. But what are the characteristics of the burst observed in light, especially in other wavelengths, for instance?
So one of the unusual, this particular event that was really interesting to us is that we had this bright optical afterglow that persisted. So this is a optical emission, which we'd known about before. We'd known about optical afterglows. But what was exciting about this particular one is that it was so bright in the very highest energy gamma rays, and we saw this link between what happened in the optical fading, and we saw a very similar fading of those very highest energy gamma rays, very similar persistence of those very highest energy gamma rays. Normally in the lower energy gamma rays, they only last for something like a minute or so. But this event went on and on in the very highest energy gamma rays, even after those lower energy gamma rays faded away. And that was a really interesting sign, this link between the optical afterglow, which we know is generated as the ejecta impacts the surrounding material. The link between this optical afterglow and these very highest energy gamma rays really clinches this idea that those very highest energy gamma rays are generated by this, what we call external shock, as that ejecta impacts the surrounding environment. So that was one of the really exciting things about this event, to see that link.
All right, appreciate it. Sylvia, we'll target this one question to you, and I'm not sure I can pronounce the word in here. We'll find out. How does this gamma ray burst compare to the Ordovician extinction event?
So first, you have to convince the people who are studying the history of the Earth that the Ordovician event was, which was a major extinction event. You have to convince them that this was actually caused by a gamma ray burst. I believe the consensus is that it's probably caused by volcanic activity on the Earth, which changes, the sort of CO2 content and contents of the atmosphere. So there's again, if the Ordovician extinction event was actually caused by a gamma ray burst, it would have had to been much closer than this gamma ray burst. It would have had to been within our Milky Way. Other than that, it's kind of hard to say because there's a wide range of different different energies you might get out of a gamma ray burst. It's kind of hard to say what sort of gamma ray burst might have caused this extinction event, if indeed it was caused by gamma ray burst. So sorry, that wasn't very satisfying, but.
No, that was great. But can I elaborate on that a bit?
Absolutely.
First, one shouldn't bring up this extinction event without mentioning Professor Adrian Malott of the University of Kansas, who is the main driver behind this idea. And he certainly intrigued my interest in it around 2005. And one thing that was most interesting is that it turns out the extinction event isn't cataclysmic and sudden, but it extends over some millions of years. And so what I did with a very talented high school student, Jeremy Holmes, is to look at the fact that you can have a 1-2 punch with a gamma ray burst. First, you have the burst and the high-energy photons come, and as Sylvia mentioned, they burn off the atmosphere, they destroy the ozone layer, all the plankton get sunburned and die away, and then there's one type of event. But then the cosmic rays start coming, and the cosmic rays have their own impact and can cause global cooling. And in a weird sense, there was some behavioral extinction that was in accord with those patterns. But as I mentioned yesterday in the telecon, since then it's been more clear that the rate of the type of gamma ray bursts in the galaxy, as John Piero said, are so rare, and the chance that the beam is pointed toward us is so unlikely that we think probably not the case, in spite of some tantalizing suggestions that they could be related to the trilobite extinction.
Appreciate it. Getting some good questions in from our Facebook followers as well as from Google Hangout. This next question, I'm not sure who can take it, but it is intriguing. How big can a gamma ray burst get? Are there upper limits in theory or in principle to the energy that they can emit?
Well, they seem to originate in massive stars, so you have an upper limit depending on the mass of the star. We're thinking that this is Rob Priest here. All the energy that is equivalent to the rest mass of the sun is converted into gamma rays. If these are isotropic events, they can't be. There's an upper limit to the amount of matter that can be converted directly into gamma rays in an explosive outflows in the jets. And so basically the upper limit is determined by the size of the star that is supposed to be the progenitor of the gamma ray burst.
I see. Charles, can you tell us another basic question, I guess, but we got a question here on it. How does the gamma ray burst actually start?
Sorry. First, let me also pick up on where Tom was, or Rob was talking about, because that was an excellent question about the most energetic gamma ray burst. It's not proven that black holes are the drivers behind gamma ray bursts. In fact, there's a very powerful school of thinking that neutron stars, magnetars, could also power gamma ray bursts. And there's lots of interesting evidence on that side. These X-ray plateaus, for example, that we see with the Swift telescope. And there, though, we know that there's an absolute energy maximum. And in a couple of occasions, that energy maximum is violated. And so that supports the possibility it's a black hole. And then if it's a collapse of a massive core of a massive star, it can be up, it can be somewhat larger in terms of absolute energy. But if they take that absolute energy, which is like the mc squared energy, where m is now the mass of a solar mass core, and you direct it into a very small jet, you can get very large energies. So there's this very difficult task of going from what we see to what really is. And because it's a beam geometry, we're just looking down the jet. We don't know how big the jet is. So that's a tricky thing to establish. But anyway, the last question was really good because it really is bearing on different schools of thought that are not yet settled. So, and now I've already forgot what you just asked, Frank.
How do these gamma ray bursts actually start?
How do they start? Oh, okay, so this is where you have a massive star. It has fuel. That fuel is burned, and it makes a massive iron core, and that core is held up by various types of pressure. Ultimately, it's neutron degeneracy pressure, but if it becomes too massive, it just collapses to a black hole. And that is the standard pathway by which we think a gamma ray burst proceeds of the long gamma ray burst variety. There's the second very important pathway where two neutron stars or a neutron star and a black hole coalesce. Those make short gamma ray bursts, and that's just as interesting. But for the burst under discussion today, it's of the long type, so related to a massive star.
Okay, now is the gamma ray burst radiation in phase, so to speak, like a laser?
Short answer, no.
Okay.
Longer answer, no.
All right. Now, is there enough energy in such a burst as the one we just seen in April that it can fuse the heaviest elements? Another question from our Facebook followers.
Well, this is Rob Priest again. I was just at a conference in Kyoto where some of the modeling of fusing into higher atomic mass elements was simulated, and it seems that to a pretty good approximation, you can get some of the highest elements produced in a supernova-like outburst, like a gamma ray burst. So the possibility is, yes, we can produce some fraction of the high atomic mass materials in such explosions.
Yeah, and let me carry on. That's a really excellent question. I don't know where because this bears on the subject of how a gamma ray burst and supernova are related. Most supernovae, after they explode, they form this nickel that decays into iron and cobalt and powers the supernova light curve. But for the gamma ray burst, there's a school of thinking that the core collapses directly to a black hole, so there wouldn't be this supernova. formation event with this nickel, cobalt, and iron. So you have to make that in a separate way. And indeed, people look at how to use the gamma ray burst radiations to produce high mass elements in order to save this sort of paradigm where the black hole is directly formed by the collapse of the core of the massive star.
Appreciate it. Tom, I'm going to send this question to you. Why shouldn't optical and gamma ray light behave basically the same? Why is there a difference there?
Yeah, so just because of the energies that the particles are accelerated to. So the optical light is generated often, not always, often by lower energy particles, and that may be accelerated in different ways from the gamma rays generating particles. But we see sort of two classes of emission. Sometimes we see a very close coupling between the variations in the gamma rays and the optical. We call that prompt optical emission. And because they're so closely coupled, we think that they're generated by exactly the same process. With this other type of optical emission, which we saw in this particular event, with the afterglow emission, that's kind of the glowing embers of the explosion, if you will. And that's not necessarily linked to the gamma rays. In fact, in this case, it was with the very highest energies, but not at those lower energy gamma rays. And that's typically what we see are these lower energy gamma ray emission in a gamma ray burst. Normally we talk about that. And often we'll see this optical afterglow persisting for a long time, way after all the gamma rays have faded away.
Okay, can someone, another question here from our Facebook fans, can you tell us about terrestrial gamma ray bursts? Are they different per se than these gamma ray bursts we've seen?
Well, this is Rob Priest. Terrestrial gamma flashes are observed by our instrument, the GBM, aboard Fermi. And they're quite different. They're thought to be runaway acceleration of electrons in very high electric fields at the top of thunderstorms. And we have actually seen traces of positrons interacting with our detectors, and so the energies involved are high enough to produce pairs of electrons and positrons. So it's a much different, purely electromagnetic phenomena, but also quite interesting in its own right.
Okay. John Piero, I'm going to target this question toward you. What do X-rays bring to the table in gamma ray burst studies?
The gamma ray, you mean?
Yeah.
Well, gamma ray bursts have been detected in gamma ray bands, or they have been discovered.
What does the X-ray spectrum bring to the table?
Oh, sorry.
What things do we learn from the X-ray spectrum?
Well, the X-ray spectrum actually are not that interesting at the end, because, for instance, we see some evolution in the X-ray spectrum in the early day, in the first few minutes, when we still seeing the dying part of the prompt emission with the X-ray telescope on board of Swift. But since then, the spectrum is always quite a slope of 1.8.2. I mean, the slope of the spectrum doesn't change over minutes, hours, and days. It stays quite constant. But this is just the band, the soft X-ray energy band. And now with new stuff, we have also some more information about another X-ray energy band that goes from 3 keV to up to 79 keV. And even there, we found that the spectrum is exactly the same from 0.3 keV that we've seen with Swift up to 70 keV. But this is also an important information as well for the model interpretation.
All right, appreciate it. Sylvia, I'd like to talk a little bit about Fermi if we can. Can you tell us what the lat gamma ray light curves say about these gamma ray bursts?
So this gamma ray burst was especially interesting in the lat because it gave us the opportunity to study something that's usually far away at a at a sort of relatively close distance. And this gamma ray burst was within the closest 5% of bursts we normally see. And normally bursts that are this close to us are kind of weak, just because weak bursts tend to happen more often. And this burst was sort of a more ordinary burst. And I think the Swift paper actually calls it an ordinary monster. So this was exciting in the high energy gamma rays, just because previously we had a model that, and we still have this model, that explains the high energy emission very well. And then we sort of found that with this burst, because it was so close to us, we saw the little bumps and wiggles that we didn't see before when the bursts were farther away from us. And so the previous models that we had still explain 90%, 95% of what we see in the high energy gamma rays, but we did detect a handful of extremely high energy gamma rays. And for these events, we required sort of we had to think back and maybe try to tweak our models a little bit, or maybe add on another thing, or just go back and try to think where how we could fill in the gaps. And because it was so close, we also observed it for 20 hours, which is over 10 times longer than the previous gamma ray emission, high energy gamma ray emission we've seen from the burst. And so just overall, this burst was exciting in the high energy gamma rays for the Fermi lat, just because it was so close and we could really see the little things that we didn't see before.
Okay, Chuck, I'm going to throw this one to you if I can. Now, we saw this humongous gamma ray burst on April 27th, but how long did it take for that energy to actually get to us? When do we think this thing actually exploded?
Oh, well, yeah, it's not quite right to say its birthday was April 27th, 2013. That's when the light came to us.
Right.
But it was born, or it died. It depends if the glass is half empty, I guess the star died. If the glass is half full, the black hole was born. I guess we celebrate black holes' birth because they're so bright and fantastic events. But indeed, that was like 3.75 billion years ago, the light travel time from this burst event to the present epoch. You know, the age of the universe is 13.7 billion years. So we call this a young burst all the same, because lots of these bursts take place at 5 and 10 billion years, and by that early time, they have to go through so much cosmic expansion that their signal becomes very weak. So this, by being only a mere few billion years old, its signal is very strong. So even though it's a nearby guy and comparatively young on all sort of geological timescales, when the Earth, was 3.75 billion years earlier on the Earth, it looked a lot different, and indeed the whole universe looked a lot different. But that's the long answer. Okay.
All right. No, I guess that prompts the follow-up question: how do you make those determinations as to how long ago it was?
Gosh, indeed, this is the important question of how to measure distance, which pervades all of astronomy. But now we recognize that the only way to make sense of the nebulae that have
Did we lose you, Chuck? Well, maybe we did. We'll see if we can get him to patch back in here. Next question I have from our social media venues is, could a GRB be considered the extinction event that seems to have occurred on Mars, meaning the disappearance of the atmosphere? Good question. Anybody?
I would say no. It's just, I mean, as we said, it's very rare event, and it's very the probability that gamma ray burst explode and the jet is pointing toward Earth or toward Mars is very unlikely. The point that Mars lost its atmosphere is because the gravity of Mars is not that strong like one we have on Earth, and therefore was not able to keep its atmosphere.
Okay, thanks. Sylvia, I'll throw this out to you. Can we assume that it's a gamma ray burst that occurs with the creation as a creation event of every black hole?
As Chuck was saying before, it's very likely that all of these sort of long gamma ray bursts happen when you have a very massive star, the core of one collapsing into a black hole. But there are other very prominent models that could also explain these gamma ray bursts. For instance, having a very highly magnetized neutron star, a very fast spinning neutron star in the middle. So it's not entirely accurate to say that each of these gamma ray bursts will lead to a black hole, and obviously a lot of black holes form without a gamma ray burst, just because it takes a sort of a very special set of circumstances to form a gamma ray burst. Did I answer the question?
I think so.
Okay.
Next question from social media is, when, according to theory, would you expect to first detect a gravity wave after first detecting such an event as this?
Well, Rob here, detailed modeling of the collapse of a massive star into a black hole or a neutron star tell us that there is a lot of material left over that's jostling around and wiggling and trying to get into the black hole, and that will produce a characteristic signature in gravity waves, coincident with the gamma ray radiation and the optical light that we see. So they should be pretty much simultaneous when we have the ability to actually detect gravity wave radiation.
Okay. John Piero, I'm going to send this one to you. What, in this particular gamma ray burst that we've seen in April, what was the beaming angle of this burst?
Well, it's difficult to say. For instance, in our paper with Swift optical data, we see a break in the light curve that we interpreted as the jet break. If this interpretation is correct, then we derive an angle of less than 3 degrees. But this break is not clear cut, so there are a discussion about it. But usually we have this kind of opening angle for this kind of source, a few degrees.
Here's another question for you, John Piero. Has this gamma ray burst actually changed any of our understandings of how stars evolve?
About how stars evolve, no, because I mean, as we said, apart from the high energy emission that has been seen by LAT and the coincidence of the first variability between the GAV emission and the optical, for the rest of the properties of the optical and X-ray light curves is very similar to the other gamma ray burst. So it's just telling us what the other gamma ray burst already told us. What it is new actually with this burst is because it is very nearby, we were able to see also the associated supernovae. And this is very important because so far we have seen supernovae associated to long gamma ray bursts only in very nearby gamma ray bursts, which were much weaker. So what the uniqueness of this burst is that it is as bright as the one we usually see very far away, but for those very far away we could not see the supernovae. So there was a discussion about how often there was a supernova associated to a long gamma ray burst, and if cosmological gamma ray bursts are actually 1 or 2 or up even 6 or 7 or 9 we have seen so far, there is no supernova. And the answer from this burst is yes. All indications now are that all long gamma ray bursts are probably associated to supernovae. And this is very important.
All right, appreciate it. We're going to have to wrap up here or get close to it. What I would like to do before we close out completely, though, is I'd like to go to each one of the panelists to get a real quick snapshot of what they thought the most important elements of this gamma ray burst finding was from their perspective, their instrument, their space telescope. And unfortunately, Charles isn't with us right now, so Tom, I'm going to start with you.
Yeah, so for me, the really exciting thing about this event was that we saw it from so many different spacecraft and so many different wave bands. So all the richness of phenomena that we have in a gamma ray burst. We had all the right things on orbit. We had them on the ground. We collected the observations of this spectacular event. So it really gives us a way to now test our understanding. And as has been said before, there are interesting twists on our understanding that are developing because we're seeing all these details. And that to me is exciting, and for many years this will be a Rosetta Stone event to test our ideas on.
Sounds good. Appreciate it, Tom. Rob?
Yes, this burst has presented a unique opportunity to test our theories for gamma ray bursts, and it has met each challenge and basically destroyed them. So we are happy to have the opportunity to compare data with theory.
Sounds good. Appreciate it, Rob. Charles is back. Charles, what I'm doing is, as we're closing out here, I was just giving everyone a chance to give a 1-minute dissertation on what they thought the most important elements of this finding was. So with that, here's your microphone.
Okay, sorry. Best laid plans in technology and all that stuff, especially for theorists, you know. But anyway, this was just a fabulous event. It was ready-made. We had all these telescopes available. It was the most fluent event ever, by which I mean the energy per area was the greatest that has ever taken place. And now it's challenging all the theories and all the way we think about these bursts. So we all get to go back to the drawing table, and happily in gamma ray burst studies, it really can still be paper and pencil type physics that can make the big inroads into discovery space. And this was a burst made for the occasion.
Thanks, Charles. John Piero?
Okay, I fully agree with what already been said, so just not to repeat the things that, I mean, important of this burst is that it gave us so many information that we will have a lot of things to work on for years to come, from one side. From the other side is that because this burst has a lot of similarity with the other burst, to give us one more proof that gamma ray bursts can be used to study the whole universe, from the backyard up to the very early young universe when it was only a few 100 million years old, because we have seen a gamma ray burst that when the universe was only 500 million years old. And we now know that when we see a burst there, a star already evolved and collapsed and died already so early on. So I think gamma ray burst, and this is a final proof, is a very good way also to do cosmology, not just only the physics of gamma ray burst.
Thanks, John Piero. And Sylvia?
Well, most of the good stuff has already been said by everyone else. Selfishly, this burst is important to me because now I can write my thesis on it, which is great. But from the high-energy gamma ray standpoint, we observed a series of record-breaking photons, photons that were gamma rays that had such high energies at such late times that were completely unexpected. And like people have been saying, this makes us go back and figure out what additions or what alternatives we need to really come up with a good model of gamma ray bursts.
Thanks, Sylvia. And that's going to have to do it for today's Google Plus Hangout. I'd like to thank the panelists for their time today. And as usual, we would like to thank you for joining us in today's event. For more information about the findings of this gamma ray burst or any of NASA's many programs and projects, visit us on the web at www.nasa.gov or via any of our many social media venues such as Facebook, Google+, Twitter, YouTube, and on. Once again, thanks for joining us and have a great day.